parametric equation of the tangent line to the curve of intersection of one surface is z equal x squared plus y squared. You let me know what is the name of this surface. And another surface is 3x squared plus 2y squared plus c squared equal 9. You give me a name of this surface. At the point 1,1, 2. Okay, that's it. Period. Help me, guys. What is the name of the first surface? This one. Surface number 1. Surface number 2. Opinion. No? For today, this is easy. Identification. The name is Maria Jose. Paraboloid. Paraboloid, in this case, circular. It's okay, because the coefficient is 1, 1, or it's the same. It's paraboloid. Cool, paraboloid. And the second one? And the second one is... No idea. Elipsoide, es obvio. Es obvio que es elipsoide. Elipsoide. Okay. By the way, this paraboloid is along what axis is along? Along what? X, Y, Z. X, Y, oh, Z. Cool. Because the verb is weird, different. Cool. So now this look like that. Oh, paraboloid. And I can do like a imitation of the level surface, no, to indicate this is surface, no. And this is ellipsoid. Ellipsoid, well, I have no idea how it look like. Well, I suppose I need to express in a standard divided by 9, but no, I don't want. I am using now GeoGebra in the last moment. And important is that you have, for example, I don't know, ellipsoid. Suppose ellipsoid like that. Oh, completely symmetric, guys. And the important thing is the intersection. Wow, no good. The intersection is a weird surface, and I don't care. It's a weird curve. It's not important. The determine the equation for this surface is very, very complicated. The most important is you have a point, a specific point in the surface, in the curve. Que es the famous point 1,1,2, que you checking, plugging in each equation and satisfy perfectly because 1 squared plus 1 squared is 2. See, it's 2. And here is 1 is 3 plus 2 is 5. 5 plus 4 is 9. Cool. So at this point satisfy both surface and also satisfy the equation of the curve in red color, but I don't know the equation for the red. Is very, very complicated, but I don't care. Basically, the thing I try to find is the equation of the line tangent to this curve. Equation of it in parametric. Okay, so now this is one application for the gradient. The gradient, is perpendicular to the surface. So suppose we have two gradients, no? You have the gradient Suppose the first surface, que C equal x squared plus y squared. This is expressed in explicit form because C is isolated, but I can express it in implicit form. You put x squared plus y squared minus C equal to 0. And you apply gradient. Gradient capital F. Let me call this capital F. Okay, this is capital F, x comma y comma z. And the gradient of the capital F is partial derivative with respect to x is 2x, comma, partial derivative with respect to y is 1, comma, partial derivative this f with respect to z is negative 1. Super. If you want, you evaluate specifically this gradient equal. I forgot the equal. This gradient I evaluate at the point 1, 1, 2. Entonces ese vector, que the vector es 2, 2, negative 1. Okay, and this vector I know que es perpendicular, is normal vector to the paraboloid. Let me try to do my best. After in the script of GeoGebra you see clear. Suppose que es something like that. Boom. This is gradient F. Okay. Likewise, I take the second surface here. It is 3x squared plus 2y squared plus c squared equal 9. This is an explicit form, and implicit you put the right hand side equal to 0. You want to call G x comma y comma z, and we compare the gradient of G. Partial derivative with respect to x is 6x, comma. Partial derivative with respect to y is 4y. And partial derivative with respect to z is 2z. And you evaluate at the specific point. Okay, the point 1, 1, 2. Entonces es 6, 4, and 4. Now we have another vector. Okay, this vector is perpendicular to the ellipsoid. I suppose, I don't know, like that. G, now like G. It's a gradient. Now it's obvious that in order to find the direction vector of the line in this direction or in opposite direction, it doesn't matter, you perform the cross product. The cross product is a fantastic tool to help me to find a new vector that is perpendicular to the given vectors. You perform the cross product nabla f, so gradient of f, cross product nabla g. The famous formula ijk, and you copy 2, negative 1 is the component of this vector, and 6, 4 is the component for the second vector. Okay, let's do it. Pero no, I skipped the arithmetic part. I know the answer. I did it. The answer is 12, negative 14, negative 4. Okay, it's perfect. And I can see, wow, this number is even number. We can divide by 2 if you want. Remember, I need the direction vector. The magnitude is not important. So you have another parallel vector que es 6, negative 7, negative 2. No? You divide by 2 this vector. And this is scaling scaling. You can use it either way. This is okay, but this is, in my opinion, better, no? Because the number is smaller, it's easier. Now we are ready to express the final answer, que es the equation, the parametric equation of the line, que es tangent line in between two surfaces. Okay, the point is given at the beginning, 1, 1, 2. So we need, remember the information that we need to define the line parameter is we need the point, and we need the direction vector. Direction vector is 60 minus 70 minus 2. Done. And who is T? T is a parameter que is from negative infinity to positive infinity because it's infinity line. Any question, guys? It's another application for the gradient. You have two surfaces, the surface intersecting each other, and you find the equation for the tangent line of this curve. Okay, no problem. Is there the case with this restricted? No, exactly. No, exactly. No, not restricted. After you see restriction in detail. This is just application. Application gradient, because the most important thing you need to remember is a gradient in 3D is a vector que es a vector normal vector to the surface. Okay, in the specific point que you evaluate. Good. Okay, no problem. Now I want to explain the one theoretical part.
Professor?
Go ahead.
Why did you divide the direction vector by 2?
Well, because I like, they are not mandatory. The differences between the vector 12, negative 14, and negative 4, and 6, and negative 7 is the same. It's the same vector. It's parallel vector, but different magnitude.
Okay, so...
Entonces, to get the equation of the line, you need any
direction vector.
Exactly.
Okay. Thank you.
Now let's move on, guys, to the one theoretical part that I would like to discuss with you. Que es, you know, no super big deal, but this is it's important because I would like you integrate in your mind the concept of the partial derivative, continuity, and differential. It's a differentiation. It's different in multivariable and the single variable. So in single variable, Cal 1, you know that I start always with the Cal 1 because I support in the knowledge que you know. Entonces I extending the idea in the multivariables and multidimension. We have two concepts, que es the concept of the continuity. And it's easy because it's a limit when the x approaches to a of the one function f of x is equal the function evaluated at the point. Basically, behind this definition, we have two things. Number one, the limit exists. Okay, sometimes, you know, fail. Second, the function exists. And both are equal. Entonces, there are a lot of examples or counter-examples in what do not satisfy this condition. I suppose que you study in detail in Cal 1. And differentiability. Well, is que this limit, there are two definitions. The most popular is that definition. So we are talking about the point A, is differentiability at the point x equal 8. See, this limit exists. Then the differentiability is one concept is stronger than continuity. Because suppose in this box, I suppose the set of the function I put inside the box, the set of the function is differentiable. And I put in this box the set of the function is continuous. Okay? So see if this function is differential, it's obvious, implied directly. Let's continue. The converse idea, no. In opposite direction, no. And the typical example is, remember, continuous in common language. So you say no in the formal definition in common language is a curve. Okay, you can drawing without listing the basic for the paper. Continuous. See, we have a hole, or we have a gap, or something to say now is discontinuous, no? Or jump discontinuous because exist, pero the limit do not exist. Entonces, discontinuous. And differentiable is more stronger concept, more stronger concept, because don't allow, it's a smooth. So in common language, it's a smooth curve. Entonces don't accept, for example, the corner like that, sharper point, because in this point, the derivative, que es the tangent line in the point, in this case, not unique. Entonces now happen exactly the same, que fail the limit. The limit do not exist because the limit is biggie. The limit is unique. When you approach it to the left and you approach it to the right, you get the same value. Nice, exists. Okay? There are a lot of examples of the function que es continuous and not differentiability, not differential. Okay? So differentiable is the most strong. And so let's move on to the, you remember that, right?
Professor? So if it's differentiable, then it's guaranteed continuous, is what you said?
Absolutely, 100%.
But I thought the sharp curves like meeting up, I thought that's not differentiable.
Exactly.
Wouldn't it still be continuous?
Okay. This graphic is continuous, yes or no?
Yes.
Okay, cool. But it's not differentiable at that point. That is a reason that exists this no implication.
Okay. Thank you.
Si es differentiable, it's because it's continuous, and smooth. Now, 100%, I guarantee continuous, right? In that direction. Cool?
Yes.
Okay, super. Now, let's complicate your life now in multivariable gal tree. On a gal tree, we have two concepts we study, que es continuous, continuity, continuous. This is the set of the function that is continuous. We have the set of the function that is the partial derivative exists. Partial derivative exists. And we have a concept I want to discuss with you now, okay, differentiability, no? Those are differentiable. Entonces now it's similar to the Cal one, so but differentiability, remember we study, I remember directional derivative, no? Que es derivative in any direction. And partial derivative is weak because partial derivative is in the direction x and the direction y. And what happened in the all directions? So it's obvious that to prove differentiability, we're using another idea. I don't want to discuss this in super detail because it's not important for engineering. This is the mathematician theoretical part, right? But okay, look, let me explain because it's not easy. Continuity is, we did before, limited. For example, when the x comma y approach to a comma b is a point of the function f of x comma y should be always f of a comma b. That's exactly the same. The limit exists, the function exists, they are equal, perfect. Continue. Now, partial derivative, well, you know, is partial derivative with respect to x and partial derivative with respect to y. As you need to guarantee complete, full differentiability, you need to the directional derivative exists. This is the idea of this. Entonces, the mathematician create this idea. Look, let me show you. You have the function. I want to prove que differentiability in any direction, no in the specific direction of the partial, and you subtracting the linear approximation. Que the linear approximation, remember, guys, is the tangent plane. I suppose you remember that. And this is the error. One interpretation of this is you have surface, suppose paraboloid. And one specific point, I have linear approximation, que es the tangent plane. Entonces now I see a lateral view of this is the parabola. This is the plane. In the neighborhood of the point, if I want to investigate if it's differentiable or no, I have the tangent plane. And tangent plane is fantastic because tangent plane is formed by infinity line. So not necessarily try infinity possibility. No. Using one dimension objects, a higher dimension, que es plane, que es 2 dimension, if you will be able to, this error is that distance, no? That distance. This is the approach to zero. So basically, the criteria of the differentiability in multivariable is you apply the limit, always is limit, guy. When the x comma y approach to the point a comma b. This is the point a comma b in xy of the error. Okay, the difference between the function and is linear approximation, okay, the tangent plane, divided by the distance in x direction, que es x minus, this is a distance formula. As you prove that this ratio is equal to 0, it's because this error decreasing faster than the approximation that you are doing in the x. So this is the strong concept of the differentiable in multivariable. This is horrible because to prove that we can do using elementary example, but it's not important. I consider it's not important. The limit, the idea is no, so find the tangent plane is easy, subtraction is easy, but you face in the last moment and the horrible limit. And you know that the limit is complicated, multivariable, no? So now, what is the conclusion? Okay, I want to explain. Exactly the same happened in the column 1. To be continuous, no imply differential. No, in this direction, no. In this direction, yes, 100%. Because using this formula, you prove that the derivative exists in any direction, not necessarily the partial. Partial is, weak because in the two classical direction. And see, to be differentiable, obviously, the partial derivative exists because partial derivative is just example of the infinity derivative you have in any direction. And entonces now, in this direction, it's obvious que no, because maybe exists the partial derivative, however, another derivative in another direction do not exist. In this case, continuous and differential and partial derivative in both directions is not necessarily 100% equivalent because there are many counterexamples to be completely false, this idea. Okay, so the thing I want to transmit, so because the majority of the book talking about partial derivative, and we use them frequently, partial derivative. And that's it. Entonces the student believe que si partial derivative exists, the function is differential. No, because maybe in another direction. No. Okay? Okay, this is the idea, guys. No, don't complicate too much. It's theoretical, pero it's important, no, to say something about that in my mind, no? Okay, let me explain another application. Any question? Do you understand this or no? You are too quiet, no? Okay, yes, okay. When I explain, for example, Cal 1, I say, well, the concept of continuous and the concept of differentiable. It's like it's similar, no, to the concept of the woman and mother. Okay, mother is a concept more strong. So to be mother, you need to be woman plus to have a child, no? So this is mother is like a differential, strong, and woman is continuous. Okay. Okay, guys, let me explain this. It's important because in the homework online you see problem about this total differential. This is another completely different idea. Differential. E. No way. Okay, this is an application in engineers. For example, or in physics, to determine how the error in the one thing is propagate in one formula. I want to explain the theoretical part too fast. In a few minutes, well, you will apply one specific example, no? Okay, suppose again, one more time, we have function, a big complicated function, and this is approximately linear approximation. And the linear approximation is the tangent plane. And the tangent plane is f a comma b in a specific point, no? Plus partial derivative with respect to x evaluating a comma b, x minus a plus partial derivative with respect to y evaluating the same point, y minus b. Okay. This is I call this like a z. I call this like a c null. Plus, let me use the other notation, partial derivative with respect to x. Evaluate a specific point a comma b. I want to call this like a delta x. And this is a partial derivative, the function with respect to y, and it's a delta y. If you, for example, move c null to the other side, we have c minus c null, I want to call delta c, is equal partial derivative f with respect to x, delta x, plus partial derivative f with respect to y, delta y. Entonces, en the interpretation in engineer, for example, delta, you consider que es error. When you measure something using rule, using specific instrument, tools, you know, okay, always the measure is not 100% accuracy, and you have error, no? So you want to study the propagation for the error inside the formula. We apply the formula. That formula is called total differential. And this formula we can extend in not only in three-dimension and multi-dimension. Suppose we have a function w that is dependent x, y, z. In that case, the supposition is that x, y, and z are independent variable, and w is the dependent variable, no? Or more. Entonces, the formula for the total differential is, you can write like a delta or d, like a differential. dw, sorry. dw, doesn't matter. In the practical applications, you suppose that dw is approximately delta w. And delta w is w2 minus w1, no? That's different. Okay, doesn't matter. Entonces es partial derivative f with respect to x multiplied by delta x plus partial derivative f with respect to y times delta y plus partial derivative f with respect to z delta z. And this is error. The error of the specific quantity that you measure using instrument. And this coefficient as a number represent the weight, how the error propagates in the formula, no? And this is the total error. Okay, si I am consequent, si you write here delta, entonces I write here delta. Okay, let's see example. Look like weird, but no. It's super intuition idea. Look. So example one, it's the only example because I want to explain one example. You have a box, and the dimension for the box is 80 centimeter. Width is 60 centimeter, and the height is 50 centimeter. So we have a box. Length, width, height. Doesn't matter what you call it. This is not important. This is totally relative. Entonces I using to measure the dimension, that dimension, one instrument, the same rule maybe, and the delta L, delta width, and delta height is the same, but it's 0.1 centimeter. It's error. Entonces I want to find surface area, for example, or volume, whatever. In this case, I put example of the surface area, the area, surface area, because my goal is to find the material I using to build this box. We have 6 faces, or I highlight only 3. Is 2 LW plus 2 LW, LH, and 2 WH. Okay, you have basically 6 faces. We have 6 rectangles. Each rectangle are twin brother, and the area is multiplication both sides, no? Entonces multiply by 2 because we have 2 identical rectangles. This is the formula. So basically, S2 is a common factor. Is LW plus LH plus WH. One way to do this in this elementary example without calculus is, well, you suppose L, for example, is equal L1, L2 to L, to length, or to width, or to height, que is the worst scenario. You suppose que is this value, 80, for example, 80 plus 0.1, 80.1 centimeter, and 80 minus 0.1, que is 79.9, no? And you manipulate the every dimension using this idea, width and height, and you could be the surface area in both a scenario, the maximum and the minimum, and you see there. Okay, This is easy. You can do that in this way. However, using calculus, we can do it in the total differential. So the error of the area is equal partial derivative area with respect to L multiplied by delta plus partial derivative A with respect to W by the error of W plus partial derivative area with respect to high delta high. Okay, let's compute partial derivative one by one. Look, partial derivative A with respect to L is equal in this equation, guys. You differentiate with respect to L. Es obvio que es 2W plus 2H. Yes or no? Because the only variable you consider is L, and the other is considered constant, no? Derivative this, derivative L with respect to L is 1. Likewise here. Partial derivative A with respect to W is 2L plus 2H. And partial derivative A with respect to H is 2L plus 2W. Okay, and now you evaluate, in this case, every expression you can factorization 2 W plus H. Entonces 2 times W is 60, 50. This is 220. Okay, now exactly the same. L plus H. 2 times 80 plus 50 is 260. 2 times L plus W. 2 times 80 plus W, que W is 60. Is 280, no? Let me check it just in case I make a mistake. Yeah, 140, yeah. 140, yeah. Okay, cool. Entonces I come back. In this case, by coincidence, the error is the same because we're using the same instrument, no? Maybe. Entonces now, and the error is 0.1. 0.1 times something, times the partial derivative gets 220 plus 260 plus 280. I can put that is 76 centimeter square because we are talking about area, no? Wow, it's too big. No, it's not too big because look, supposed to compare, see the thing we're doing is good or no. Let's compare the area. Okay, the area is just the multiplication, no? The multiplication 2 times L plus W plus H. Is area is equal to 2 times is sorry, mistake, is that formula. Entonces es 2 times, okay, let me erase this. 2 times what? 2 times 80, or common factor, 80 times 60 plus 80 times 50 plus 60 times 50. This is super easy. And the area is, wow, it's a big number, right? It's 23,600 centimeters square. Okay, entonces how you express the area, surface area, is error 1? Okay, You copy like that. Area is equal 23,600 plus and minus 76 centimeter. This is centimeters cubic, square, sorry. Everything is square. If you want to separate, you subtracting plus and minus, subtracting and addition is 23,676 is the maximum value, centimeter square. And the minimum is 23,524 minimum. Okay? Either way, guys, you can use it without calculus. So using just arithmetic. Each dimension, you compute the maximum minimum. You put in the formula and you compute the maximum and minimum area. No? However, the magic of the calculus is that you using the total differential formula. The partial derivative indicate what is the weight that this error propagate in the formula. In this example, they are not different. Too big difference between two procedures. However, in another more complicated scenario, more complicated formula, it doesn't make a difference. Okay, using the partial, the total differential formula. Do you understand a little bit? This is no big deal. This is easy or relatively easy. It's you know, is I never put the sample of this in the test, but in the homework online, yes, and the test online, yes, and the homework in the test, yes, because it's application important for you, engineer, no? How we can determine one specific formula, the propagation for the error. Okay, cool. Okay. Now, this is super important moment. This is, we come back again to the things, same thing that we discussing in Cal 1. In Cal 1, the professor explained differentiation, first derivative, second derivative, first derivative, second derivative, and after application and the maximum minimum, no? Maximum minimum. So I want to apply maximum and minimum also a multivariable. So let me recall quickly, because it's very, very confusing. The teacher explained Cal 1, don't explain clear the idea for the optimization. It's Cal 1 optimization. We have two problems of the optimization. Without constraints, okay, important, without constraints. What mean without constraint? Well, that means we have no restriction. So the function, for example, you have a function, suppose a function like that. And to say now we have no constraint. That means you suppose we analyze everything in all real number from negative infinity to positive infinity. And so my goal is find the local max mean. Okay, or another name associated in the book is relative. Relative is a synonym to local. Local max, local mean, or relative maximum, relative mean. Okay, this basically is not the higher number or the smaller number. No, it's a number that change the behavior. For example, my function increasing, and here we have a critical value. Critical value 1, because the derivative is 0, no? Remember the critical value, critical value. You compute the critical value when the first derivative of the function is 0 or do not exist. It's obvious that we have in that point a horizontal tangent line, this is critical value because the derivative is 0. And here we have another. And this is max, and this is mean. And here we have another critical value because critical value 3, because it's obvious que ese corner or sharper point, entonces the derivative do not exist. Okay, entonces this is another candidate to be critical value, ¿no? Entonces now there are many ways to prove que es máximo o mínimo. I like so much, y we use in Cal 3 the second derivative test. Okay. The second derivative test say, for example, you find the second derivative expression and you evaluate in the critical value 1, you get negative value because remember the interpretation of the second derivative is the concavity. Any function that is concave down, the second derivative is negative. As it's concave up, the second derivative is positive. For example, when you evaluate the second derivative and the critical value CB1 is negative. That indicates minimum, local minimum, no? You evaluate in the critical value 2, the answer is positive because the concave is up and this is maximum, local maximum. So you evaluate in the critical value 3 probably do not exist. But it's not important. This is not important for us. The important for us is know when the derivative do not exist and is when the derivative is 0. Cool? Do you understand this idea? You remember very well this, no? Theo is a yes. But I want to complement the idea. Complement. Like is with constraints. With constraints. What mean that? Well, okay, we don't like all real number. No. We restricted the analysis in one specific region, in one specific domain. Suppose que I select one interval, AB. Let me highlight. Include both endpoints, guys. Include both endpoints. Include both endpoints. And suppose que my function, the piece of the function inside this interval look like that. This is just example to illustrate the idea. Okay. Entonces now, likewise, you need to remember one theorem that is called extreme value theorem. Extreme value theorem. Que this theorem say if the function f, que es this function, is continuous, at the interval a comma b, include both endpoints, close it, then exist max and mean, but in this case we are talking about global, or another name is using is absolute. Es sinónimo. Es la que es sinónimo local and relative, absolute and global. Global. This is A, global. And what's that? Well, this is the large, so the global max is equal, no, imply, or it doesn't matter, equal the large value of the function inside the specific, no, region. And global mean is the smallest value inside. How we compute that? It's a little bit different to the local max, local min. Okay, the strategy is, I want to explain that. Well, I find the first derivative, no problem. You put equal to 0, you convert to equation, and you solve it, and you find the critical value. In this case, the critical value is this critical value. Okay, I want to call critical value 1, another critical value 2, and critical value 3. Because it's a point in which the tangent line is horizontal and the derivative is 0. So you have in your hand critical value 1, critical value 2, and critical value 3. Perfect. And you apply the second derivative test? No. No. You create a list. This is the important moment. And you evaluate everything. What means everything? You evaluate the critical point into the function. The function evaluating critical value 1. The function evaluating the critical value 2. The function and the critical value 3. And also in the endpoint, NA and B. And you select what is the large value, is the global max, and what is the smallest value, que is the local min. And this is a stupid example. I suppose que the large value is in B. So this is the max. And the minimum is obvious que is this in critical value min. But this is dependent example, no? You take the small number and you take the large number, the greater numbers. Do you understand very well this idea of the two constraints do optimization problem without constraint and with constraint? Cool? Do you remember or no? Sorry, I don't want to see. Sorry, somewhat. I don't want to see apply the second derivative test when we have constraint. No, have no sense. Okay, let's move on to the multivariable calculus 3. It's similar. Okay, look, we have function. So cal 3. Let's explain without constraint. No constraints. We have function c equal f and x comma y. Entonces now, in order to determine the critical value, well, I know, okay, any surface, suppose a surface like that, suppose this is the local max, local min, the gradient in this point is 0 vector, yes or no? And the gradient of this and this point is 0 vector. Do you see in the animation in the last class, when you go to the peak of the hill, the gradient disappear? Why disappear? Well, no, because remember the gradient point in the direction que the function is increasing faster, no? Now, si you go to the peak of the hill, entonces the gradient is totally lost because I have no gradient because in what direction increasing? No, see, I have the peak of the hill. Entonces I reach that, no? Entonces no, the gradient is 0 vector. Entonces it's super easy because to find the critical value, you compute a partial derivative. So basically gradient is 0 vector. That means que es the vector 0,0. So you find the partial derivative x equals 0 and partial derivative y equals 0. And this is the, in this case, a system, no? It's a system, system of equation. Unfortunately, sometimes this system of equation is non-linear, and this is very, very complicated, the algebra. When you solving, you spend 2 weeks doing this system. Now, wow. So when you come back to the problem, you don't remember calculus 3. Therefore, my recommendation, I want to explain in detail. Don't worry for this. You solving the system. It's a system. In this case, no big deal because it's 2 variables. It's 3 variables, more complicated. A system of, but sometimes it's non-linear. Wow, of non-linear. Sometimes no, sometimes linear. But see, we are talking about playing something. But no, see, it's non-linear because the majority of the scenario non-linear equation is always is complicated because there are no specific strategy for solving this. I try to bring example here. Okay, we can solve it by hand. But you need to be aware that we have Wolfram Alpha. Wolfram Alpha. Wolfram Alpha is a software online, similar to GeoGebra, but Wolfram Alpha is powerful. And which you put a system, a non-linear system, and Wolfram Alpha solve everything. Okay? In the test, you're using Wolfram Alpha. Don't worry for stupid algebra. It's not important for us. No. Okay? Okay, now, okay. So I have in my mind, in my hand, the solution for this system. Give me a critical value, CB. Critical value 1, critical value 2, critical value 3. I don't know how many critical values we have in the solution of this. And so you need to apply the second derivative test. Remember, this is a problem without constraints, no restriction. Cool. So now the second derivative test. The second derivative test is a little bit weird and multivariable, but I want to explain in detail. Look, is you compute one thing. Okay, it's actually not the second derivative, you know, it's the combination of the second derivative. You copy D. Who is D? Dx comma y is discriminant. The discriminant is the technical name of this. Discriminant. Because it's used into classification. Entonces, say si es máximo, si es mínimo, si es another thing. Entonces, now, si discriminant, bueno, the formula for the discriminant is the combination, second partial derivative with respect to x2 time, multiplication, y minus fxy squared. Well, actually, it's like a fxy time fyx. You know, it's the same. That's the reason that you put a square. Either way. So you believe that this expression is complicated to memorize? No. You remember in this format, like a determinant. Look. fxx, fxy, fxy. And this is d, like x. You multiply this and this, plus, and you multiply this and this, minus. Okay. Now the most important one. When you get this discriminant, if the discriminant evaluate at the specific point, okay, I want to investigate. Remember, we have different points. I need to evaluate one by one. See a positive value, and the second derivative with respect to x participate now alone. Evaluate the point. It's also positive. That means I want to erase that package. That means okay, we are in front relative mean. Let me try to interpretation this. And the relative means, suppose that one partial derivative is like that, and another partial derivative is like that. Suppose this is fx and this is fy. Both is, you know, concave up. So it's minimum, right? It's a some idea, no? Intuition. If the AB is also positive, it's important, and this derivative, second derivative, evaluate at the point n negative, entonces relative max I suppose that in this situation happens something like that. One derivative like that, another derivative in another direction like that. Both derivative is suppose que es parábola, ¿no? No necesaria parábola, pero es a curve. Es up and down, entonces es relative maximum. And that's it, no? That's it, no? It's more complicated. If discriminant evaluate the specific point is negative, wow, automatically you see that this is no maximum, no minimum. It's called saddle point. Okay, I want to explain it now. Saddle point. Saddle point, guys, is no maximum, no minimum. It's a point in the graph. You can see, for example, suppose that one derivative is in this direction. This is partial derivative with respect to x. And another partial derivative with respect to y is like that. And it's a saddle point. The typical example of the saddle point you see after in the GeoGebra is the hyperbolic parabolic. Hyperbolic parabolic is z equal x squared minus y squared. Have a saddle point at the point 0, 0,0. Because it's a combination, it's hyperbola and parabola, and one open up, another open down. If you want to illustrate in a few seconds. And if discriminant evaluate the point S0, we have no conclusion. No conclusion. Okay, it's a big picture of the max min without constraints. Local max or relative max, relative min, and new concept que es a saddle point. Wow, saddle point. I don't see it before in my life, saddle point. Okay, entonces now let's see example to understand much better this, no? Okay, example of the max min without constraint. Suppose that function, example one says f of x comma y is equal x squared plus 5y squared plus x squared y plus 2 times y cubed. Okay, entonces I need to investigate max min or saddle point, que es the new idea. Okay, we try. Okay. Bueno, you compare the gradient equals 0. So you partial derivative the function with respect to x. The derivative is 2x. That part is 0. That part is 2xy, xy, and derivative this with respect to x is 0. And you enforce it to be 0, that part. Do you follow me with the partial derivative? That you are strong, no? Doing partial derivative, right? And partial derivative with respect to y, let me see, let me try to understand this. This is 0, this is 10y, plus partial derivative with respect to y is x squared, and partial derivative with respect to y is 6y squared. And you enforce it to be 0. Cool. And to say in this moment, we have a system of equation, algebra. System nonlinear, of course. You see exponent 2, system of equation, wow. Okay. And you try to do your best. The problem I put here is no big deal, but some problem is horrible. You, for example, you take the first equation. This is equation 1, this is equation 2. You take the first equation. Yes, 2x plus 2xy equals 0. And you factor out y no 2x. We have 1 plus y equal to 0. To apply the zero factor theorem, x is 0 and y is negative 1. Cool. Entonces hay substitution in another equation, and the complicated equation is the equation 2. One by one, no? Of course. Suppose at x equals 0, one of the equation 2 is 10y plus x squared plus 6y squared equals 0. Suppose at x equals 0. My equation is now reduced like a 10y plus 6y squared equals 0. Oh, it's easy. It's a quadratic equation, but it's incomplete quadratic equation, so I can do that by factorization. Factorization y, 10 plus 6y. One more time, you apply this, the zero factor property. Y is 0. 10 plus 6y equals 0. Es obvio que y is equal -5 or 3 after this isolate and reduce and lowest term. Entonces, let me condensing this information here. This information is look. You copy. I try for 0. This is the problem of the system of equation, no linear. Say we confuse. At least I confuse it. So we have 0, something and 0, something because we're using this only information so far. Entonces 0, because this 0y is an -5/3. This is critical. I don't know si es máximo, si es mínimo or saddle point. I don't know. Let me try now at y equal -1. Pero plugging in this -1 and the second equation again, no? And the second equation, remember, is this. Entonces, I suppose in my mind que y es -1. Entonces, -10 plus x squared plus -1 squared is 1 is 6, no? Equals 0. Therefore, wow, we have one equation that contains only one variable. Nice, I like that. Entonces, x squared minus 4 equals 0, no? It's easy. This equation is easy. This equation is x equal plus or minus 2. Everyone knows that. Entonces, we have 2 more points. Okay, at that point are 2, -1 and -2, -1. You see, because the supposition was y equal -1. So we have the list of the critical value are the list and the no constraint, not necessarily write the list, but I like to write the list in order to organize my word, no? Comma 0, -5/3, comma 2, -1, comma -2, -1. Boom, 4 critical value. Well. Now this is the moment in which you apply the second derivative test and multivariable. And the second derivative test, wow. You compute the collection of the second derivative. We have 4 second derivatives. Okay, the collection. You compute. Oh, let me see. You compute ffx, fxx. You compute fyy. And you compute, bueno, fxy, that by the way is always in the opposite direction. Okay, those are moving to this expression. Okay, I deduct the first derivative, and you find the second derivative with respect to x. It's 2 plus 2y. Everyone follow me? You consider x as the only variable and y is constant. The derivative, okay, cool. You take this expression now, and you differentiate with respect to y. The answer is 10. The x squared is a constant, derivative is 0, and 12y. This is the second derivative, double derivative with respect to y. And xy, I take, for example, the first one again, and differentiate with respect to y. The first part is constant, the second part no, and thus the answer is 2x. Because 2x you consider the constant, and derivative y with respect to y is 1. Cool? Now, using this information, we compute the expression for the discriminant. The expression for discriminant is multiplication who? 2 plus 2y times 10 plus 12y minus square this guy is 2x squared and 4x squared. Okay, if you want FOIL, I want to avoid the algebra because it's too easy for us. It's a 20 plus 44y plus 24 x squared, y squared, sorry, y squared minus 4x squared. I know it's too long, and you evaluate this discriminant one by one and the potential point that we have. So you evaluate d and 0, 0. You evaluate d and 0, negative 5 over 3. You evaluate d and 2, negative 1. You evaluate d and negative 2, negative 1. Okay, the arithmetic part I want to skip. The answer is 20. Well, it's obvious. It's obvious. Okay, and 20 is positive. Good, I like that. The other is 40 over 3. It's also positive. And the other is negative 16. Okay, negative. Automatically, when you get discriminant negative, the classification is saddle point. Okay? Saddle point. Cool. Now, in order to differentiate max or means, you evaluate here, for example, you evaluate my function xx and the specific point, que es 0, 0. Let's move. En 0, 0 es obvio que es 2. Es obvio que es 2. Look at that here. It's 2. And 2 is greater than 0. The conclusion is the mean, local mean, relative mean, the way you want to call it. And you evaluate fxx again at the point 0, negative 5 over 3. And the answer was negative 4 over 3. K is negative, and that's mean, K is local max. End story. Well, that's it. No, we can do a little bit more, but this is easy. But yes, curiosity, you know, you evaluate in this specific point in the original function in order to determine, well, it's a maximum. Okay, it's a maximum at 0, 0, but what value? So now you evaluate in the original function 0, 0. You evaluate 0, negative 5 over 3. It's at the same point, but on the original function, not in the discriminant. And this guy, this guy. And the answer was wow, I don't copy that. The answer is, you see, well, the answer is 0. It's obvious it's 0 here. Well, I don't copy, guys. You see, well, okay, there's a number. But this is a mean, this is a max, I suppose it's bigger. And this is a saddle point, I don't care. Entonces now, okay. I don't want to waste the time with this operation. Now, let's see the geometry idea of this function in GeoGebra. Okay, I create a script for this. Let me try. Yo, relative max. Okay. Do you see? Do you see, Giorgio? Do you see? Okay, yes. Okay, let's focus, guys. I copy in the first line the original function. Yeah, I copy in the rest of the line. Ah, look at that. We have the answer here. You copy in the rest the point A, B, C, and D. Remember the first point was 0, 0, and the answer is 0, so the C value. And the 0, negative 5 over 3 is 125 divided by 27. And the saddle point is 2, negative 1 and negative 2, negative 1, the answer is 3. And graphically, let me try to understand this. Look, this is my surface. Look, I want to flash it. This is my surface. And this is the famous 4 point. Wow, es obvio que this guy is a local max. Es obvio que this guy is a local mean. Look, let me rotate to see more clear. Okay. No obvio, pero you can see que this and this together is a saddle point. And the saddle point, you see, let me try to make a zoom to see que in the saddle point, for example, it's weird because here we have like a saddle. Saddle is like a seat that you put inside the horse, no? Saddle point. O sea, es in what direction, for example, in what direction the partial derivative is positive, in another direction the partial derivative, in direction x and direction y, is negative. This is saddle point. Do you see or no? Do you see, for example, in the maximum, everything is open down. So the parabola, or not exactly parabola, the curve, look like parabola, open down. That is the reason it's maximum. And this open up. Let me rotate to see more clear. Open up. But in this case, no. In this case, open, maybe weird. Open in that direction up and the direction down. This is typical saddle point. Do you see? Cool. I like calculus 3. Okay. Okay. That's it? No. Of course not. I have the problem, the same optimization problem, but with constraints. What mean constraints? Let me try to, we have no time to finish this because it's too long, but let's try to write the problem, no? You understand a little bit. Do you see what more? Do you see what more? Do you see? Okay, cool. Okay, look, suppose you know we have function. Example 2. This example 2 is with constraint. Okay. Entonces now I have the function it's given. Similar to the problem with without constraint. Okay, cool. But the constraint is given now. Okay, the constraint is x in between 0 and 5. So I don't want to optimize. No, in all real, no, in R2, in XY plane. No, in one piece, in one portion. Because in the real life, that portion, que es the constraints, is the important, is the interesting part. And the rest is stupid, it's contradiction, right? Entonces now, let me try to do a sketch about this region. No? This region is, let me try here, XY. This is 0, 5, 1, 2, 3, 4, 5. 1, 2, 3. This is my region. Okay. Entonces, the idea is very similar to the idea in Cal1. Look, in Cal1, we have one interval, AB. Okay, this interval is a segment. This segment is one-dimensional object. And we include the boundary, okay, the endpoint. So this is dimension 1, because it's a segment. And the boundary is dimension 0, because it's a point. Now, in this case, no. In this case, the area, so the interval is no interval. It's an area enclosed, and there is a rectangle, no? It's two-dimensional. It's rectangle. However, the boundary is one dimension, okay? It's the segment line can enclose. Do you see? It's important, guys. You see the analogy, because that's the same in calculus, but you extending the dimension. But what should I do? Well. First of all, I try to do my best, similar to the problem of the constraints. So you compute the gradient, you compute partial derivative f with respect to x, partial derivative y, you enforce it to be 0, and you compute the potential point. See, this potential point I computed using the system lie inside this. Oh, it's good. See, it's outside. I don't care. Okay, it's doing. Partial derivative is 2x minus y equal 1, minus 1, sorry, equals 0, minus 1 equals 0. Okay, it's 2x, here is it's constant, this is y, and this is 1. Okay, and this is 0. Okay, now the partial derivative with respect to y is 4y minus x minus 3 equals 0. Wow, equation 1, equation 2, but this is easy because these equations are linear, and solution for the linear we are doing 3,000 in our life. You organize the equation. 2x minus y equal 1. Wow, nice. Equation number 1. And you organize in the same column minus x plus 4y equal 3. Equation 2. You solving using, elimination, substitution, matrix, because I organize elegant. And the way is the column of the x, the column of the y, and the right-hand side number. I don't want to explain this because hello, the answer is x equal 1. Solution, the system is x equal 1 and y equal 1. Wow, 1, 1. And 1, 1 is the point 1, 1. And 1, 1 lie here. Boom. 1, 1, 1, 1. Intentionally, I create this example, that this critical value belong to the hour restriction. Therefore, I need to consider inside the list, right? I need to consider inside the list. Okay. So remember, in the constraint problems, you compute the critical value. Okay. See, the critical value lie in the area, in the region. You consider it like one candidate to be a global max, global min. However, I need to evaluate in the boundary, and this is the complicated part. Because where's the boundary, professor? One of the boundary is that segment. Look, that segment. Okay, that segment, and that segment, and don't forget the endpoint. So any corner is important. Let me use a different color. The red one, the blue one, include this. Another color, green maybe. Okay, and another color maybe yellow. I know that this problem is too long, but it's no big deal, it's easy. Let's try to do at least one, because the time is over, almost over. Suppose que I travel for the trajectory red color, que es on the x-axis. Therefore, in the x-axis, y0. Okay? Yeah, I plug in the function, y0. What function? The original function. And the original function with the y is 0, you have the function evaluate at 0, y. Y0. Any point here is 1, 0, 2, 0, 3, 0, 4, 0, 5, 0. Okay, you evaluate here. Entonces you have x squared minus x. Because y0 is the ally only this guy. I want to call f evaluate n1 of x. To call another name, you know. But this is cal1. So you convert the problem from 2 dimension to the 1 dimension, because it's a segment. And you investigate, for example, in the middle of this red segment, we have maximum, local, or minimum. And you find the derivative. The derivative is 2x minus 1. And you enforce it to be equal to 0. Okay, cool. At x equal 1/2. Okay, suppose que here, 1/2. We have another potential point. Okay, 1/2, que actually is 1/2, 0. Okay. And also, you take advantage to evaluate in this topic the function and the endpoint, que es 0, 0, and 0, 5. Don't forget the corner. So I convert the problem, the 2 dimension in 1 dimension. You navigate for the red segment. I investigate in 1/2. We have a critical value, 1 critical value. I don't care if it's maximum, minimum. Let's see. You are in the corner. And the corner is obvious. Let me see. 0, 0 is 0. And 0, 5. Oh, 0, 5, no, sorry. 5, 0. Hello, I am crazy. 5, 0. Because on the x-axis, 5, 0. When you evaluate, when you replace in the original function, x for 5 and y for 0, the answer is 20. Okay. So now we continue next time. We continue for the blue, for the green, and the yellow. We create a big list. And this big list that you evaluate everything at the original function, and you decide what is the large number, global max. What is the smallest number, local min. End the story. Okay, cool. We continue Friday. Friday is an important day. Friday is important day. Okay, entonces no, porque the people are absent Friday, no holiday. Okay, guys, have a nice day. We continue Friday.